Thanks for coming so early. Initially I didn't plan to do this, and Trip Collins was supposed to talk about waves, but Trip had some issue with visas. He was in Australia, and thing happened, and so he couldn't make it. So I'm filling in for Trip on the buoy side, and then since I was here, I say, well, why not talk about altimeters, the good old nadir altimeters, going back all the way to Skylab, that was flying the first satellite altimeters. And the design from that actually influenced all the altimeters that are flying up to today. And then Alejandro will tell us about things which actually have inherited from Mars missions doing interferometry. And also I will be going back looking at buoy and how we've gone from pretty big platforms, which are still being used, especially for weather, wind, and temperature, pressure, and many other measurements. So this is why you need a pretty big platform. Going all the way down to smaller and smaller buoys, and cheaper ones, which is good for some things, but you also have to keep a critical eye on the quality of the data. And although the spotters are fantastic, they're still not as good as a data well. So just don't throw away your data wells. They are really good. All right, so let's get started. All right, so first I'll talk about buoys and measuring waves with floating buoys. So it may sound a crazy thing for anybody else who's not in this field to measure stuff at a moving surface. But since we're studying waves, we don't have much choice. And so we have to deal with the fact that our measurement system is moving up and down and back and forth. And ideally, if you want to capture the waves, you would like to have the waves move like a water particle. And in reality, it does not really do that. And pick this nice animation from DataWell that kind of shows this pretty well. And I had it somewhere on this screen. Where was that? Oh yeah, this guy. So that movie was made by DataWell. They had some fun making a small version of a DataWell and put it in the lab. In this tank, so they just vibrate the vessel up and down. So that's Faraday excitation for the physicists among you. That you can make some nice oscillons and lots of funny physics, but that's not what they're after. Basically, what you see is that when you don't have any buoy here, you get some kind of small waves, but it doesn't move much. And they're going to introduce a buoy in this at some point. Here you go, a model buoy with a hole in it. And so you see, the buoy is not quite following the water particles, right? And for all of you that have developed buoys, I don't know if Eugen is here, but he'll talk about his buoy later on. We've played the same game with Pedro Guimaraes as part of his PhD in the lab in Brest. And the shape of the hull, and there's many things that actually contribute to the response of the buoy. And of course, there's a resonant frequency for the heave motion. It's even more true for spar buoys that have some kind of heaves. All people have done ocean engineering know about this kind of stuff. And if you don't have the fender, see what happens. So the fender around the buoy is actually pretty useful. And this is one of the reasons why the spotter have this kind of funny shape around them to kind of prevent and damp this vertical heave motion. But as you go to high frequencies, you can excite the resonant frequency of the buoy, and you get this kind of crazy stuff. So yeah, buoy doesn't quite behave like a water particle. And then you can look at the response to that. So you have the link to the full video in the talk, so you can go back to that. And I'm just going to move on to the rest of my talk here, if I can. Okay, I'm going to stop this guy. Yeah, that gets crazy. Come on, stop. No. I'm not sure I can stop this. Yeah, buoy's dead. All right, affichage. There you go. So the size of the buoy matters, and so at the end of this video, you would see that these are the response, actual measurements of waves with real wave riders with a diameter of 0.9 meter, 0.7 meters, and the smaller wave riders, 0.4 meters. And you can see that as you go to smaller diameters, you can go to higher frequency waves. Typically, the good old big data wells kind of crap out at something like 0.6, 0.7 hertz. And anyway, they give you only the spectra up to 0.6 hertz. With the smaller ones, you could go maybe up to 1 hertz, and that's kind of pushing it. And that's the thing you have to deal with. That's the hull, that's the response of the hull. Then you have to put a sensor in this thing to actually measure the waves. So there's many ways to do this, data wells use this heave sensor, which is gimbaled, so it's sitting on a thing which is making it stable. So that's the reason why you don't want to roll the buoys, because otherwise you kind of break the system, and you offload it from the truck. So these are sensitive things you don't want to mess too much with. More recent buoys based on GPS would use GPS velocities, not actual GPS position, but the velocities from the GPS signal, which potentially is more sensitive for lower frequencies. Or you can also go to using accelerometers. And so in the buoy we developed in the lab with Pedro, we have actually different versions of accelerometers, some pretty high-end ones, like a couple €1,000 MEMS systems, which are pretty accurate. And otherwise, you can do the same GPS and accelerometers that you have in your phone. And you can actually put your phone in a bag and dump it in water, measure waves with it. If the waves are big enough, it works pretty well. It's not a problem. I just also want to point out that these measurements are semi-Lagrangian. So they are the same as the Eulerian measurement, only for the linear part. Hopefully, they're measuring something like the B spectrum, if we talk about what Miguel was showing yesterday. I'm not sure it's exactly that, and I would like some theoreticians to look at this problem. What is a buoy actually measuring compared to the real thing? I think they're capturing the modulations, but not some other part of the second order term. So I think there's some interesting work to be done to really clarify what are the buoys measuring compared to fixed measurements. But maybe somebody knows the answer to that, so I don't. Yes, I need to minimize that big thing there. It's floating. All right. So typical buoy would measure, so let's talk about data well, 3 components of the acceleration, the vertical acceleration, AZ, and the 2 horizontal acceleration in the X and Y directions. But any sensor that measure 3 components like these 3, or pressure, U and V, or the heave and the slopes, SX and XY, or the U and V from the GPS. From these type of 3 time series, you can go to an estimate of these first 5 directional moments of the directional spectrum. So here you have the directional spectrum, EOF and theta, that thing here. And so this guy is just our usual heave spectrum. You can also call that A0. And then if you take the integrals with a cosine inside, or a sine, or cosine 2 theta, or sine 2 theta, then you get this A1, B1, A2, and B2. And these are coming directly from the cross spectra and the spectra of the 3 time series. So we have 3 time series, 3 spectra, 3 co-spectra, so that's 6 pieces of information. These are the first 5 related to the directional spectrum, and then the 6th one is a check ratio. And this actually was the stuff that was plotted on one of the Datawell nice movie things, and you'll see that the check ratio is a very nice quantity to check if your buoy is measuring waves or doing some funny, goofy thing. So theoretically, this is only a function of water depth, and if it's in deep water, it's equal to 1. You have the same amount of motion on the vertical as you have on horizontal, and if you don't, it means that your buoy is doing something funny. So it's always something good to do. CDIP, for example, does a very nice job of having all the check ratio together with all the first 5 moments. Not all the data centers provide them, so be careful about that. Right. What's next? Nope. Doesn't want to go forward? What do they do? All right, so unfortunately, or fortunately, I don't know, many people have a hard time with these first 5, and they would actually like to see a directional spectrum. But I just want to warn you again and again, from an information point of view, basically at each frequency, you're only measuring 5 parameters. So if you want to get a directional spectrum, say, at every 10 degrees, you need 36 pieces of information. So you go from 5 to 36, and when you do that, you're just making stuff up, right? And so there's statistical methods to make stuff up and estimate directional spectrum for the first 5. And I will just want to go back on that because people are still using some of these. And I really want to emphasize that the first one is really the ugly method. Nobody should do this, any paper using that should be rejected, right? And this is just, Longet-Higgins said, well, let's say that A1, A2, and so forth are just the first terms in the expansion of the Fourier series of directional spectrum. And that turns out to give you pretty bad and really broad directional spectra, right? The next two, we could argue. My point is that the MLM is bad because it basically, when you compute the directional moments, sigma 1 and sigma 2 from the MLM spectrum, you don't go back to the values you actually measured, but you're biased. So this is a biased estimator, and I don't think, and you have to use that very carefully. And one thing which I think is better, but never perfect, because you're always making stuff up, is using the maximum entropy method from Ligre and Krogstad. And actually, Michel Benoit has a very nice review of these methods back in a paper from '97, I believe. Also, there's an MEM2 and other stuff, so I really encourage you to go back at Michel Benoit's paper from '97. All right, so let's talk about the ugly. And this, I really want to shame the people that wrote this. One of them may be with us. Fabrice, you're here? So there was a very nice paper for the other part, which was looking at Sentinel-2 imagery and looking at currents and wave measurements. And at some point, they compared buoy measurements to Sentinel-2 derived spectra. And then they say, well, yeah, we see this very nice two-swirl nicely separated. And that stuff was estimated with this method from Longet-Higgins. The SQs they found, so I think it's Maria Jurovskaya actually did that on the NDBC website. They used to give the formula from Longet-Higgins. I don't know why they did this. I don't know what they thought by doing that. And so some people that would go to the NDBC website and say, oh yeah, I could use that formula for getting directional spectrum. Looks fun. Okay, you get the mean direction, but that's about it. If you actually do it properly with MEM, and we corrected that plot in a paper with Bia, this is what you should get with MEM and not that ugly thing, right? So, I apologize. No, I don't apologize. So I'll be the nasty reviewer too if you ever try to do that to me, and your paper will go through the trash. All right. Okay. So yeah, Ian was arguing that MLM had a tendency to artificially broaden the spectrum, but it does not produce pure peaks. Oops. And this is one of the issues with the MEM, is that sometimes, because it's making stuff up, it would actually, especially when things are noisy, it may have a tendency to give you some funny peaks. But what I would add is, if you actually use MEM, it also has a tendency to fill the gap between the two lobes, and you produce a bimodality, which is really not as strong as what we think it is. And that's one of the problems we have with. But anyway, these directional spectra estimates are just pretty pictures. These are not scientific things you should use for science, I think. And there's obviously other methods. So Mark Donen and others have proposed this wavelet directional method. So basically, you look at the time series, and you would say that at any given time, there's only one wave train coming from at one frequency. So it's actually a really nice method for picking out faint peaks that may be coming from the sides. But it's not producing a directional spectrum in the sense that its moments would be what would be measured by the buoy directly. So I think that method actually could be modified to not have the bias on the spreads, but if you use it as such, it would give you spectra that are too narrow. All right, so the first five, A1, B1, A2, and B2, you can actually convert them to something which may be a little more easy to understand. It actually is a two-way conversion, so you don't lose information from going the first five to these theta 1, sigma 1, theta 2, and sigma 2. As you could go back and forth from one to the other, so that's a nice property. And yeah, the 270 and all the stuff here is so that I have, my convention is that I have the waves coming from in nautical convention, because I'm a coastal guy initially, so I always plot my spectra with wave coming from. Sorry for the other guys that do it the other way. You always have to be careful about conventions, about directions. And so you have this is a mean direction, so that's pretty straightforward to understand. This is a directional spread. This is another mean direction, and this is another directional spread. And also want to point out that there's always noise in the measurements, and so the noise will bump up the directional spread, and so you have to be worried about that. The NDBC buoy are infamous for being a bit more noisy than the data wells, and there's this nice paper that Bill O'Reilly wrote back in '96, and with that he made a lot of friends at NDBC. Okay. So how to interpret this, these spreads? Oh yeah, and by the way, before I forget, there was people yesterday using all sorts of definitions for directional spread. All right, fun. You can do whatever you want, but these are the only spread you can measure with a buoy. So please, if you have to use a measure for spread, use one of these two. Otherwise, people will get confused. Yes? I'm going to talk about it right now. Thanks. So what is the difference between sigma 1 and sigma 2? Yeah. And until a couple years ago, I never really paid too much attention to sigma 2. It was kind of a nuisance to try to understand what it means. And so if you make a simple exercise of having a spectrum which is made up of two Gaussian peaks, so in that case, I have these two Gaussian peaks separated by delta theta, and the width of the sigma of each of these Gaussian is 10 degrees. And then I'm going to vary delta theta, and we're going to look at how the sigma 1 and sigma 2 change. So this is what happens if you go from delta theta equals 0. So you only have basically one peak, and you see that the value here is nicely 10 degrees. So this parameter sigma 1 is actually the sigma of the Gaussian if you have a Gaussian spectrum, which is nice. As you separate them and they get further apart, so that you see at the beginning, sigma 1 and sigma 2 have the same value. And then they separate, and then sigma 2 has a maximum, which is square root of 2 divided by 2 in radians, which turns out to be something like 40 degrees. And sigma 1 will increase all the way to 82 degrees, which is square root of 2 radians, right? And what's very interesting is, so basically this guy gets maximum when the two components are 90 degrees from one another. So if you have two narrow peaks that are 90 degrees apart, that's the maximum value you can get from sigma 2. Whereas sigma 1 is maximum when you have the same amount of energy traveling in the opposite direction, right? So that's the difference between sigma 1 and sigma 2. Now, can we actually make sense of some measurements and some models in that sense? And maybe yes. So I took again the example I was showing on Monday of these simulations with GQM and the other source terms, looking at directional spectra. And then if you actually integrate these, so this is, that's the directional spectrum at 1 Hertz. And if you compute sigma 1 and sigma 2 at 1 Hertz, you would see that you go from that value to this value, okay? And from that one to that one. And so you can see that as a function of frequency, here sigma 1 increases, especially with Romero's dissipation and the GQM. And here sigma 2 first increases towards mid-frequency and then decreases. And the point I want to make is that this decrease is actually due to that fact here. And that means actually that if we think there's like two narrow peaks in the spectrum, and they're getting further and further apart at higher frequencies, the fact that we have sigma 2 going down means that the separation is more than 90 degrees. Of course, the spectrum is just not two narrow peaks because there's stuff in the middle. So it's a very idealized way to think about it. But this is just to show you that when you're looking at bimodality and directional spreading of the spectra, sigma 1 is interesting, but sigma 2 is also equally very interesting. And that's something I never realized until 2 years ago. And if you look at buoy data, you can find some cases where that's the case. So this is, yeah, it's a very messy plot, I'm sorry. So the top plot is, so we have buoy data here up to 0.6 Hertz. This is a data well buoy station Papa. So I want to thank again Jim, I think Jim is online, Thompson, for having that buoy and maintaining it. It had some failure last summer, so Jim was telling me that he's planning to put back in. And so that's sigma 1 going up, and then sigma 2 goes up and then starts going down. And you can see the different flavors or different source terms with GQM and Romero's parameter dissipation gives you something that may be too narrow or doing the same kind of stuff or going up and down. So there's some really interesting value in looking at sigma 1 and sigma 2. Okay, my point is that sigma 1 and sigma 2, you can measure them from buoy directly.
Yeah, but they use the sigma 2 with a plus sign. 1 plus the square root.
Okay, I don't know. Thank you for, I didn't know that. Yeah, we can do it.
Okay, that's clear for sigma 1 and sigma 2, but how do we spread? Sigma 1 and sigma 2.
Yeah, I'll leave that off during the break. Well, this is, I think theta 1 is pretty straightforward, mean direction. Theta 2 is a mean, but with 180-degree ambiguity. So when you have a difference between theta 1 and theta 2, what does it mean? Well, it means that maybe you get some stuff in opposite direction. Or some, yeah, it's not clear in my mind yet. So, all right. So there's still some value using MEM and plotting directional spectrum to see what it may look like, but it's just a possibility that what it may look like. It's just, pretty pictures. Okay, and one thing I also want to touch on is the uncertainty of any measurements, actually, not just buoy. And this paper, I actually had it, but I never really looked at it so carefully until last year by Ian from '86, looking at the probability distribution of spectral integral. So, for example, if you measure significant wave height, what is the uncertainty on the significant wave height, just based on the sampling errors? Because you've seen yesterday or the day before that we have wave groups, right? And so groups will modulate things. And so if you measure wave heights over any record of length tau, you're bound to have some variability of the wave height from one record to the next record. And the nice thing is, if you assume that waves are nicely Gaussian, well, the surface elevation is Gaussian distributed variable. So its PSD, its power spectral density, will have a chi-square distribution. And any spectral component will have a chi-square distribution, and because the total energy is a sum of all the spectrum, so we actually have a sum of chi-square distribution variables, so it's also chi-square distributed, and hence, yeah, that's the total energy is chi-square distributed, and so the wave height, which is square root of that, is going to be chi-distributed. And the nice property of these chi-distributions is that there's a nice ratio between the standard deviation and the mean, and that's given by the number of degrees of freedom with some funny earlier gamma functions. But you can figure out that the variance of the wave height over a record length tau will be going to be given by this kind of expression, in which you have the wave height comes in, and there's some interesting parameter, which is a spectral pickiness parameter, which is the integral of the spectrum squared, divided by the integral of the spectrum squared, but the square is outside. So you can predict, theoretically, what should be the standard deviation for wave heights just due to groups. And I'll come back to that at the end. Okay, so some other funny cases, not just exactly buoy. A couple of years ago, we went away and debunked some crazy papers about scattering of waves in ice. There's a whole literature about wave scattering that should be super important, and the pinnacle of that effort was to discuss the fact of infragravity waves propagating across the Arctic. That should do some crazy scattering, and you should get strong attenuation. So I talked to Peter Adams about that, and he had some nice data in that place. So we're close to the North Pole, the ice edge is here, and there was 2 big storms in 2007. That was part of a big EU project in the Arctic. And so these are actually the 2 biggest waves of the 2 biggest storms of the year in the entire globe, I think. And they sent swell of 23 seconds all the way under the ice, all the way to that measurement location. And what they had here is not a buoy, but 2 tilt meters measuring the tilt of the ice in 2 directions, x and y. And so you only have 2 time series, so you can do just 2 spectra and 1 co-spectrum. But from that, you can still do A2 and B2. And so you can compute a directional spread, which is sigma 2. And so this is the measurement of the power spectral density from these 2 storms arriving. So the swell is arriving on 13 and 14 of February. So you can see it starts pretty low frequency, pretty close to 0.03 hertz. So we're talking about 27 seconds there, and all the way to something like 20 seconds. And you can see that in the sigma 2, the spreading, it's pretty low, below 10 degrees. So people that say that there's a strong scattering of waves, especially long waves, bye-bye. It's your dream. Data doesn't support that. And you can model that, and if you put scattering in the model or strong dissipation, you try to tune the scattering to get the right wave height. And of course, if you have scattering, the waves will ping-pong and pinball around the Arctic for days. So you have these, you have 2 days of energy because it's just Anderson localization, if you want, at the Arctic scale. But the measurement doesn't show that, and you can actually model the spread with just a relatively simple anelastic wave dissipation, so to take into account the bending of the ice flows to look at that. All right. Another case, just to show you that buoys are fantastic. This actually started with a tweet about the Hunga Tonga observation, and somebody looked up at the Ifremer archive of all the SAR images and found that example. And these big crests here you see are the tsunami from the Hunga Tonga that exploded 2 years ago in that place. That imagette is from here, and so it's traveled something like a couple hundred kilometers. And the wavelengths of these guys is actually not very far from swell, but it's definitely not swell. And so I looked that up, and I was looking for buoys to say, well, can actually confirm this from buoy measurements, and CDIP has a station in American Samoa. So Hunga Tonga is here, American Samoa is there, and this is where the buoy is. So it's not in deep water, right? You have to live with that. But if you look carefully at the wave height for waves longer than 25 seconds, you get infragravity waves, right? And then you get that event. And this is it. This is a tsunami at Hunga Tonga. The single wave height over, I think it's 30 minutes records. I have the raw data, so I have to redo that, but I never found the time to do it. So it's about 6 centimeters wave height. And if you look at in spectral density, this is the spectrograms. So this is frequency and time, and you see that event here. This is this guy, and this puts the noise floor of the measurement below 0.0001 meters squared per hertz, which means that the noise floor for this wave height more than 25 seconds is less than 4 centimeters. So wave riders buoys are really, really good. Now, we're trying to do similar stuff now with SWOT data and spotter buoys. I have a poster about that event out there. So there was a big storm I talked a bit about on Monday in June last year. So that was the peak of the storm, and we have buoys in all these circles there. And this buoy B here, so initially I was looking, well, what is this? And so I put a log scale so you can actually see what's happening. So you could argue that this might be the noise floor of the measurement. And here, there is something which is definitely higher than that, and my model with reflection actually is capturing this, and the model without reflection doesn't. This is at buoy B, this is at buoy G, and this buoy actually is probably getting waves reflected off Cape Lewin and sent back. Looking at directional from the buoy is actually pretty hard, because directional moments are more noisy. And this is just to show you that noise floor here might be around 0.02 meters squared per hertz. So it's really not as good as a data well, but good enough to do a lot of nice work, because we have all these buoys around. And if you want to know more about buoy quality, we also tested the Swift buoys with Jim Thompson. This nice paper by Guimaraes et al. 2019. All right. Yeah, that's more stuff about the buoys. And yeah, I'm not going to talk about SWOT, because Alejandro's going to talk much more about SWOT right after. So I just want to say a few things about nadir altimeters, which may seem like something from the past now, but not quite. So the idea is that you have a radar in space on a satellite, which is sending pulses on the surface. So you have a satellite here, and you send pulses there. And at some point, you have the wave front of your radar waves will touch the surface, and then you start to get some echoes, and you record that echoes. And as the satellite moves from here to there, then you're going to get a different surface below it, and you're going to get different echoes. And of course, you see me coming. I've plotted this big, nice wave group behind it. And so what's happening with wave groups? So if you actually simulate this situation, this is the waveform you would get at the bottom of the wave group, and this would be at the top of the wave group. And you see that in that case, you get something like 1.6 times the wave height. In that case, you get 0.1 times the wave height, the significant wave height. So this h hat, which is what you're getting from fitting a waveform to the measurement, is not quite the significant wave height, which I think it should be, but it's some kind of local wave height at the scale of the groups when you have these kind of groups. And what's happening is, so this waveform, so that's the power of the echo as a function of distance or time. So here I convert to distance. So that would be the mean sea level, and then this is mean sea level plus my amplitude of the waves, and then twice that, and then that's above. So you first get the echoes above, and then you get the echoes after the mean sea level. In theory, the waveform should depend on the radar beam pattern. So here I've taken a very broad beam for the CNES purist people that don't want to see this kind of stuff. And it should also depend on the PDF or the surface elevation, or more exactly, because any piece of the surface which is not flat towards you is sending the radar stuff in that other direction, back to space. So what you're actually sampling is a surface at only a surface at the points that have zero slope when you're looking straight down. Any other piece in the surface is sending radar waves in the other directions. So you can think about what that means. We're actually not sampling the full surface, which is causing a sea-state bias, and you can compute that from these lambda things from Shrokos in theory, and we try to look at that. But the funny thing is, if you have a skewness in the surface elevation, or if you have wave groups, you're going to get a distorted waveform. And yeah, I'm going to skip over that. Right, so what's happening when you have wave groups? Can you mute these guys online? All right, so the reason why we get this type of waveform, to the theory by Brown from 1977, to derive that, you assume that you have the same Gaussian distribution everywhere, and just sum this Gaussian distribution coming from all the pieces of the ocean, and that's giving you the echoes. And this is actually is the same thing as saying that your waveform is a sum of a Gaussian plus another Gaussian and another Gaussian, all shifted because the points that are away from nadir are shifted in space, right? And so the sum of all these Gaussians is just this Nye error function waveform in black. Now, if you have some perturbation of the wave height locally, and so instead of having this dashed line, you have this solid line, you get some perturbation in the waveform, which is going to be this, pink line. And basically, so the waveform is the black plus the pink, which gives you the red line. So instead of having a nice brown waveform, we get some perturbation. This isn't what's happening if you have a perturbation at nadir, and you can quantify the magnitude of the perturbation with the ratio of the wave height in that perturbation and the wave height outside. And this R naught is telling you if the perturbation is at nadir or away from nadir. And by the way, this is exactly the same plot as Haynes' plot for the effect of skewness in the PDF of the surface elevation. And so the presence of wave groups seen through the waveform is exactly the same as the effect of the skewness. And yeah, this is theoretically you can actually derive the waveform for that perturbation of the wave height. So if you have a perturbation of the wave height here, it doesn't matter if it's localized here or around a ring, because for the altimeter everything is kind of summed up on these rings. And we get this waveform, which is a brown waveform plus some perturbation, which the amplitude is a function of the ratio of the wave height inside and outside the perturbation, and the area of that perturbed area compared to the total area of the footprint. All right. And yeah, just a minor remark. If you look at the skewness effect in Haynes, it has this lambda, and our A thing is just lambda divided by 6, which means that if our A is 0.3, the skewness is impossibly large as something like 1.8, something is skewness that you never see. Right? So just to say that the effect of the wave group is actually much stronger than the effect of the skewness. And then the way we actually estimate wave heights and sea level from altimetry is by minimizing a cost function between what we measure, the waveform, and what we think is the waveform. And sigma h is just essentially the wave height by the 4. And so when you minimize that, you're going to estimate the wave height by finding the sigma h that gives the minimized minimum of the cost function. So that's the most simple least square cost function. You can make some other choices that will give you different answers. And with the least square, with this perturbation, what you find is that the wave height the altimeter estimates is a true wave height, significant wave height, plus some effect of the perturbation with these A and B coefficients. So again, A is the amplitude of my perturbation of the group, and B is the distance where the perturbation is compared to the nadir. So that's some kind of normalized range. So this is at nadir, this is away from nadir. And so you can do the same for the sea level. So in that case, we expect that the wave group should change the wave height, right? If you have locally some larger wave height, that should reflect in a true measurement. The thing is, for the wave height, you find that this perturbation is 0 at nadir. So it's kind of funny that if you put a wave group right under the satellite, the fitting will not see it, but it will have an impact on the sea level, and that's an error because we have a mean sea level which is flat, and so this is a tracker error. So you have a tracker bias in the estimation due to the fact that you have wave groups. And so how does it work? So if you take a piece of the ocean, surface elevation, you compute the envelope from that, and this dashed line is a circle with a magic radius, which is half of what's called the Shelton radius, which is the square root of the altitude of satellite times the wave height times 2. And that is actually what scales these perturbations. Yeah. All right, so that's the envelope. What we're saying with our theory is that basically you should multiply this by this filter function. So all these perturbations from the mean wave height is going to be multiplied by this JH filter, and this is what you get. And if you integrate that in azimuth, you get this distribution of impact of these local wave groups on the wave height estimation. And in the end, so you would just do the sum of all the distance from nadir, you get one number, and that will give you the estimation of the wave height. So, so this is our theoretical view of looking at how the altimeter works, and is that view actually correct or not? Then I'm going to do that for many, many points over that surface. I'm going to estimate wave heights without retracking the waveform over all these points. And this is a correlation between the actual retracking and our theory for how the altimeter works. And it's not perfect, and Alejandro was puzzled by that, because we're essentially, our theory is just based on the envelope, but of course there's a phase. And when you count for the phase, and you change the phase, it actually explains the thickness of this cloud here. So the altimeter, of course, is not only seeing the envelope, it's actually seeing the true elevation, so it can be positive or negative. And if it's positive or negative, it has a different impact, right? So I'm going to skip over all of that. You can actually now remove the wave groups and find the currents in SWIM CFOSAT altimeter data. This is a paper we published last year with Marine de Carlo. And I just want to comment that instead of doing it with this very simplified waveform, you can actually do that for real waveforms and more theoretically advanced waveforms, and also with the Wales retracker, which is a weighted least square average. So it's different from the least square because it's actually going to give more weight towards points in the beginning of the waveform, which gives actually a response in terms of the JH filter that has a maximum closer to nadir. So it actually gives you a high resolution in terms of measurement of the wave heights and a lower speckle noise. I didn't talk about speckle noise. That's the other big source of variability in these measurements, but I'm just going to leave it there. I also want to emphasize that this Wales retracker is actually the reference algorithm for the ESA State CCI project. Because of these things, it allows a higher resolution than the usual Willis square. It reduces the group-induced noise in the sea level. And very important, it's an open source piece of code. So you can go in, you can check things, and do your own retracking and change things, right? Yeah, I'm going to skip that. Just one comment on this. Delayed Doppler altimetry. Since cryosat, we have these delayed Doppler altimeters. A lot of these work on that has been based on waveforms for retracking them that are based on a frozen, not moving ocean. E pur si muove. The ocean is moving, and that changes the waveform. And you can look at that paper. And so the people that have been doing this work is Louis Marié and Frédéric Nouguier. In a nutshell, yeah, that's just a result. So this is the previous waveform for retracting. We had the Samosa model. And you get all these different things, and you can see that the orbital velocities and the proxy for that here is the wind speed actually change the waveform, and that has an impact on wave height. So to conclude, we should always know as much as possible about our instruments, even if we're modelers or theoreticians. And having open source processing pipelines is great because you can actually go in and see what's being done. Whenever possible, use measurable parameters for your analysis, for your parameterization. If you want to do a parameterization of dissipation, why use a crazy sigma defined by some crazy stuff which cannot be measured? You might as well use these two. Buoys are good and getting cheaper, but they're not perfect, so you have to be careful about that. Altimeters are amazing things. They're actually the only sensors are provided what I think are reliable measurements with very large wave heights. And beware with the DDA SAR mode data because they are not properly validated nor understood, and that's something we're fighting in as part of the C-State CCI project, how to actually reconcile the new data which is not properly defined. And that's all I have.